Hello and welcome. Wherever you are and whatever hour it is where you are, take a moment to get settled. Dim the lights if you can. This is a 2.5-hour journey through the entire history of the universe, from the first fraction of a second to the galaxies, stars, and stardust that make up everything known to exist today, including you. There is no need to stay awake for all of it. If this is the kind of video you use to fall asleep, that is exactly what it is here for. The narration will continue, softly and steadily, whether you are listening closely or drifting off somewhere around the second chapter. Most of us were taught, at some point in a single sentence, that the universe began with an event called the Big Bang, a kind of cosmic explosion that sent matter flying outward into empty space, and that empty space has been getting bigger ever since. That description is close. It is not, however, quite correct, and the true account turns out to be considerably stranger and considerably more precise than that one sentence suggests. There was no empty space waiting to be filled. There was no explosion in the ordinary sense of the word. Space itself did not yet exist to explode into. Time itself, a past leading into a future in the way it is ordinarily experienced, appears to have begun at that same moment, alongside space, rather than stretching backward forever into some earlier eternity. Over the next 2.5 hours, this account will proceed slowly, and in order through 5 chapters, exactly as the sequence is presently understood by physicists and astronomers, from the almost unimaginable first instant of existence, through the formation of the first atoms, the release of the universe's first light, the ignition of its first stars, and the slow, patient construction of the galaxies, clusters, and cosmic web that surround us tonight. Everything described here is drawn from the same body of observational evidence that has been tested and confirmed across many decades: measurements of ancient light, the composition of stars, the motion of galaxies. Nothing has been added for effect. It is, as far as is currently known, simply what happened. There is no requirement to follow every detail. Let the information settle in gradually, chapter by chapter, and if the eyes grow heavy before the end, that is entirely appropriate. The universe took a very long time to form everything now visible in the night sky. There is no reason to rush the telling of it. As mentioned a moment ago, there is a point, some 13.5 billion years in the past, before which the very concept of before appears to lose its meaning. This is among the more difficult ideas in the natural sciences to hold in the mind, and it is worth approaching slowly, without hurry, and without the expectation that it will resolve into something simple. The universe, in its present form, had a beginning. Space itself, and time itself, appear to have originated together at a single moment, rather than time stretching backward indefinitely into an empty past. What came before that moment, if the word before can be applied at all, remains one of the most contested and least understood questions in physics. The framework most widely supported by observation is known as the Big Bang model. It is, despite its popular name, not the description of an explosion occurring within a pre-existing empty space. There was no cavern of nothingness into which matter was suddenly cast. Rather, the model describes an expansion of space itself, beginning from a state of extraordinarily high density and temperature, in which the very fabric that we now call space-time began to unfold. Every point in the present universe, if one were to run the expansion backward, converges toward this same origin. This is a subtle distinction, and one worth allowing to settle before proceeding further. The universe did not expand into space. Space itself came into being and has continued to stretch in every direction ever since. Physicists describe the earliest interval of this expansion using a unit of time so small that ordinary experience offers no useful comparison. This interval is known as the Planck time, approximately 10 to the negative 43rd power of a second. Before this threshold, the known laws of physics, including general relativity, cease to provide reliable predictions. Gravity, at this scale, is believed to behave according to rules not yet fully understood, in which quantum effects and the curvature of space-time become inseparably entangled. This period is referred to as the Planck epoch, and it remains, at present, beyond the reach of any confirmed physical theory. Researchers pursuing frameworks such as loop quantum gravity and string theory continue to explore what might have occurred within this interval, though none of these approaches has yet been confirmed by observation. It is worth pausing here to consider what is actually being described. At this scale, the familiar distinction between space and time, so intuitive in ordinary life, may not have applied in the way it does today. Some theoretical treatments suggest that time itself, as a directional flow from past to future, emerged only as the universe cooled and expanded beyond the Planck epoch. Under such treatments, asking what happened before, this moment may be a question without a coherent answer, in the same way that asking what lies north of the North Pole fails to describe a meaningful direction. This is offered not as a settled conclusion, but as an illustration of how thoroughly the ordinary categories of thought can break down when applied to the universe's earliest instant. Following the Planck epoch, the universe is believed to have entered a phase known as the Grand Unification epoch, lasting until approximately 10 to the negative 36th power of a second after the initial moment. During this interval, 3 of the 4 fundamental forces that govern the universe today, the strong nuclear force, the weak nuclear force, and electromagnetism, are thought to have existed as a single unified force, indistinguishable from one another. Only gravity is believed to have separated earlier, during the Planck epoch itself. The framework describing this unification, known as Grand Unified Theory, remains an area of active theoretical research, and no complete, experimentally confirmed version yet exists. Nonetheless, the general principle that the forces observed separately today were once unified under the extreme conditions of the early universe is well supported by the broader pattern of particle physics, in which forces are observed to unify at sufficiently high energies within laboratory experiments, though at energies far below those of the Grand Unification epoch itself. At the close of this epoch, the strong nuclear force is understood to have separated from the electroweak force, marking a transition sometimes described as a phase change, analogous in certain respects to the freezing of water into ice, though occurring under conditions of temperature and density that have no true counterpart in ordinary experience. This separation released a substantial quantity of energy, and it is thought to have triggered, or at minimum coincided with, one of the most consequential events in the early history of the universe, a period of extraordinarily rapid expansion known as cosmic inflation. The theory of cosmic inflation, first proposed in the early 1980s, describes a phase during which the universe is believed to have expanded by a factor of at least 10 to the 26th power, and possibly by a considerably larger factor still, within an interval lasting only a small fraction of a second. To place this in some perspective, a region of space smaller than a single proton would, under this model, have been stretched to a size larger than the presently observable universe, within an interval of time too brief for light to cross the width of an atomic nucleus. This expansion is not understood to have violated any physical law, including the constancy of the speed of light, because it was space itself that was expanding, rather than any object moving through space at a velocity exceeding that limit. The theoretical motivation for proposing such an event arose from several long-standing puzzles in cosmology that the standard Big Bang model, without inflation, struggled to explain. Among these was what is termed the horizon problem. Regions of the observable universe, situated at extreme distances from one another, are observed to share nearly identical temperatures and densities, despite appearing, under the standard model alone, to have had insufficient time to exchange energy or reach thermal equilibrium with one another. A period of inflation, occurring before the more gradual expansion that followed, would allow these regions to have been in close contact prior to the inflationary event, thereby accounting for their present uniformity. A related puzzle, known as the flatness problem, concerns the observed geometry of the universe, which appears, according to precise measurement, to be flat, or very nearly so, across the largest scales presently observable. Under the standard model alone, such flatness would require an extraordinarily precise initial condition, one considered statistically implausible without some additional mechanism. Inflation offers a natural explanation, in that any initial curvature would have been stretched to near flatness by the sheer scale of the expansion, in much the same way that the surface of a balloon appears increasingly flat to an observer standing upon it as the balloon is inflated to an enormous size. The precise physical mechanism driving inflation remains a subject of ongoing investigation. Theoretical treatments generally propose the existence of a scalar field, sometimes referred to as the inflaton field, whose properties under the extreme conditions of the early universe produced a form of negative pressure, driving the accelerated expansion. As this field is understood to have decayed, its energy is believed to have been released into the production of matter and radiation, in a process termed reheating, which restored the universe to a state of high temperature and initiated the more familiar gradual expansion that has continued, in modified form, to the present day. It is appropriate, at this point, to acknowledge the limits of present understanding with some care. Inflation, while supported by a range of indirect observational evidence, including detailed measurements of the cosmic microwave background that will be discussed at length in the later part of this account, has not been directly observed, and its underlying mechanism remains a matter of theoretical proposal rather than confirmed physical law. Several distinct models of inflation have been developed, differing in their specific predictions, and observational data collected in recent decades has served to narrow, though not yet fully resolve, the range of viable possibilities. This uncertainty is not a weakness particular to cosmology. It reflects the genuine difficulty of investigating conditions so far removed from anything reproducible within a laboratory on Earth. By the conclusion of the inflationary period, at approximately 10 to the negative 32nd power of a second after the initial moment, the universe is believed to have consisted of an extraordinarily hot, dense, and rapidly expanding medium, populated by a continuously interacting mixture of fundamental particles and radiation. The electroweak force, which had remained unified through the grand unification epoch's conclusion, is thought to have persisted for a further interval until a subsequent transition, occurring at approximately 10 to the negative 12th power of a second, during which it separated into the distinct electromagnetic and weak nuclear forces observed today. This transition is associated with the Higgs field acquiring a non-zero value throughout space, a development that is understood to have endowed many fundamental particles with mass, in a mechanism confirmed, in its broad outline, by experimental results obtained at the Large Hadron Collider in the early 21st century. At this stage, all four fundamental forces recognized in contemporary physics, gravity, the strong nuclear force, the weak nuclear force, and electromagnetism, had separated into their present distinct forms. The universe, still far smaller and vastly hotter than at any subsequent point in its history, continued its expansion into what is termed the quark epoch, a period during which the fundamental constituents of matter existed in a state unlike anything observed under ordinary terrestrial conditions. It is to this period, and to the remarkable sequence of transformations that followed within the universe's first full second of existence, that the account now turns in the second part of this documentary. It would be reasonable to assume that a single second is too brief an interval to contain anything of real significance. In ordinary experience, very little of consequence happens within a second. The interval addressed in this second part of the account, however, spans less than that single second of elapsed time, and within it occurred a sequence of transformations that determine the essential composition of the universe observed today, including, as will be discussed shortly, the very reason that matter exists in any quantity at all, rather than having annihilated itself completely in the universe's earliest moments. It is a period during which conditions of temperature and density far exceeded anything achievable within any terrestrial laboratory, and much of what is understood about it rests upon a combination of theoretical extrapolation and indirect experimental confirmation, drawn from particle accelerators capable of recreating, briefly and on a minute scale, conditions approaching those of the early universe. At the opening of what is termed the quark epoch, the universe consisted of an exceedingly hot and dense medium in which quarks, gluons, electrons, and other fundamental particles moved freely, without combining into the more familiar composite particles that characterize matter today. Quarks, under ordinary present-day conditions, are never observed in isolation. They are confined by the strong nuclear force within composite particles such as protons and neutrons. In the extreme heat of this early period, however, the energy of the surrounding medium was sufficient to prevent such confinement, and quarks are believed to have existed instead within a state known as a quark-gluon plasma, a form of matter that has since been recreated, briefly and on a vastly smaller scale, within heavy ion collision experiments conducted at major particle physics facilities. As the universe continued to expand, its temperature declined correspondingly, in accordance with the general relationship between the volume of an expanding medium and its temperature. At approximately 1 microsecond after the initial moment, the temperature is estimated to have fallen to a point at which quarks could no longer move freely, and the strong nuclear force began instead to bind them permanently into composite particles. This transition, referred to as the quark-hadron transition, marks the beginning of the hadron epoch, during which quarks combined, in groups of 3, to form protons and neutrons, alongside a wider variety of short-lived composite particles collectively termed hadrons. It is at this stage that one of the more persistent puzzles in cosmology becomes relevant, namely the observed imbalance between matter and antimatter. According to the standard model of particle physics, particles and their corresponding antiparticles ought to have been produced in precisely equal quantities during the earliest, highest energy period of the universe's history. Under such conditions of perfect symmetry, matter and antimatter would be expected to annihilate one another almost entirely as the universe cooled, converting nearly the whole of the available mass into radiation, and leaving behind a universe composed overwhelmingly of light, with only the faintest residue of matter, insufficient to form stars, planets, or any of the structures observed today. This is manifestly not what occurred. The observable universe is composed, so far as can be determined through careful measurement, almost entirely of matter, with antimatter appearing only in trace quantities, produced through specific high-energy processes rather than existing as a primordial population comparable to that of ordinary matter. The explanation for this asymmetry, termed baryogenesis, requires some mechanism by which slightly more matter than antimatter was produced, or by which matter and antimatter behaved in subtly different ways during the universe's earliest moments. Theoretical work by the physicist Andrei Sakharov, published in the late 1960s, identified three general conditions that any successful explanation of this asymmetry would need to satisfy, including a violation of certain symmetries between matter and antimatter that has since been observed, in modest degree, within specific particle interactions studied in laboratory experiments. Nonetheless, the precise mechanism responsible for the full scale of the observed asymmetry has not yet been conclusively identified, and it remains among the more significant open questions in fundamental physics. What can be stated with confidence is the outcome, for every roughly 1 billion matter-antimatter pairs that annihilated one another in the early universe, converting their mass into radiation, a slight surplus of matter on the order of 1 part in a billion survived. It is from this comparatively small surplus that the entirety of the observable matter in the present universe, including every star, planet, and living organism, is understood to derive. Following the annihilation of the greater part of the universe's matter and antimatter, the Hadron epoch drew to a close at approximately 1 second after the initial moment, as the temperature fell below the threshold required to produce new hadron-antihadron pairs. The universe then entered what is termed the lepton epoch, during which electrons, positrons, and neutrinos, collectively known as leptons, came to dominate the composition of the universe, alongside the small residue of protons and neutrons that had survived the preceding annihilation. As with hadrons, electrons and their antiparticles, positrons are understood to have annihilated one another in overwhelming numbers as the universe continued to cool, leaving behind a comparatively small surplus of electrons, sufficient, in combination with the surviving protons, to eventually form neutral atoms at a much later stage in the universe's development. It was also during this general period, at approximately 1 second after the initial moment, that neutrinos are believed to have decoupled from the remainder of the cosmic medium. Prior to this point, neutrinos interacted sufficiently often with other particles to remain in thermal equilibrium with them. As the universe expanded and its density declined, these interactions became increasingly infrequent, until neutrinos ceased, effectively, to interact with the surrounding matter at all, and began instead to travel freely through space, largely unimpeded, as they have continued to do ever since. This relic population, termed the cosmic neutrino background, is predicted by theory to permeate the universe to this day, though its extremely weak interaction with ordinary matter has, to date, prevented its direct detection, distinguishing it from the cosmic microwave background, which was released at a considerably later stage and has been measured with great precision. With the conclusion of the lepton epoch, at approximately 10 seconds after the initial moment, the universe entered a period during which conditions became suitable for a further transformation of considerable significance, the formation of the first atomic nuclei heavier than a single proton. This process, termed Big Bang nucleosynthesis, occurred over an interval lasting from approximately 10 seconds to approximately 20 minutes after the initial moment. A window determined by the balance between the temperature required for nuclear fusion to proceed and the temperature above which newly formed nuclei would be immediately broken apart by high-energy radiation. During this interval, protons and neutrons, present in a ratio determined by processes occurring slightly earlier, combined to form deuterium, an isotope of hydrogen containing 1 proton and 1 neutron. Deuterium nuclei, in turn, combined further to produce helium-4 by a substantial margin, the most abundant product of Big Bang nucleosynthesis, alongside smaller quantities of helium-3, lithium-7, and trace amounts of a small number of other light isotopes. The relative abundance of these elements, as predicted by the theory of Big Bang nucleosynthesis, depends sensitively upon the density of ordinary matter present in the universe at this time, and the close correspondence between predicted and observed abundances of these light elements stands as one of the principal lines of evidence supporting the Big Bang model as a whole. It is worth noting, with some care, that Big Bang nucleosynthesis produced only the lightest elements in the periodic table. The process could not proceed further, to the formation of carbon, oxygen, iron, and the wider range of heavier elements upon which later chemistry and biology would depend, because no stable nucleus exists at atomic mass 5 or atomic mass 8, creating what is termed a nucleosynthesis gap that could not be bridged under the rapidly cooling and expanding conditions of the early universe. The elements heavier than lithium would not be produced until considerably later within the interiors of stars and, in the case of the very heaviest elements, within the extreme conditions produced by the deaths of massive stars and the collisions of dense stellar remnants. This account will return to that later, stellar chapter of elemental formation in the fourth part of this documentary. By the conclusion of Big Bang nucleosynthesis, at approximately 20 minutes after the initial moment, the universe had cooled to a temperature no longer sufficient to sustain further nuclear fusion on any significant scale. Its composition, by mass, consisted of approximately 75% hydrogen and 25% helium, alongside only trace quantities of heavier light elements, a ratio that has been confirmed with considerable precision through astronomical observation of the oldest, most chemically unaltered structures presently known. This composition would remain essentially unchanged, on the largest scales, for a very considerable period thereafter, as the universe entered a long era dominated not by matter, but by radiation, during which the energy density of light and other electromagnetic radiation exceeded that of matter, shaping the dynamics of cosmic expansion until the two contributions gradually approached parity many thousands of years later. The universe, at the close of the second part of the account, remained far too hot for atomic nuclei to capture and retain electrons, and existed instead as a dense, opaque plasma, through which light could not travel freely. It would remain in this state for a considerable further period, expanding and cooling gradually, before conditions finally became suitable for the formation of the first stable, electrically neutral atoms, and for light, for the first time, to travel unimpeded across the universe. It is to this transformation, and to the faint and ancient light that it released, that the third part of this documentary now turns. It might be assumed that once matter existed, in the form established during the second part of this account, light would have been free to travel across the universe immediately in the way it does today. This was not the case. For a considerable period following the events already described, the universe remained in a state that would have appeared, to any hypothetical observer, uniformly opaque, and the eventual release of that trapped light, when it finally occurred, left behind a signal that can still be measured today in every direction, across the entire sky. Free electrons, not yet bound to atomic nuclei, interacted continuously with photons, the particles of light, scattering them repeatedly and preventing them from traveling any appreciable distance before being redirected. A photon released within this early universe would have traveled only a short distance before colliding with a free electron, altering its course in a process termed Thomson scattering. The practical consequence of this continuous scattering was that light could not travel freely across the universe, and the cosmos as a whole existed in a condition broadly analogous to the interior of a dense fog, through which no clear image could be transmitted across any significant distance. This condition persisted for approximately 380,000 years, as the universe continued its gradual expansion and cooling. Eventually, the temperature of the cosmic medium declined to approximately 3,000 degrees on the Kelvin scale, a threshold at which the energy of the surrounding photons became insufficient to prevent electrons from being captured by atomic nuclei. Protons, in overwhelming number, began at this point to capture free electrons, forming stable, electrically neutral hydrogen atoms. A smaller proportion of helium nuclei underwent a comparable process, forming neutral helium atoms. This transition is termed recombination, though the name is, in a strict sense, somewhat imprecise, Since electrons and protons had not previously existed in a combined state from which they might recombine, the term has nonetheless persisted within the scientific literature by long convention. The formation of neutral atoms had a consequence of considerable significance, with electrons no longer present in a free state throughout the cosmic medium in appreciable numbers. The scattering of photons that had previously rendered the universe opaque ceased, almost abruptly, on cosmological timescales. Light, for the first time since the universe's earliest moments, became free to travel across space without continuous interruption. This moment is referred to, with a certain evocative accuracy, as the epoch of photon decoupling, and the light released at this time has continued traveling through the universe in every direction ever since. That light has not vanished. It persists to the present day, though its character has been substantially altered by the intervening billions of years of cosmic expansion. As the universe has continued to expand, the wavelength of this ancient light has been stretched correspondingly in a process termed cosmological redshift. Light that was released at recombination as visible and infrared radiation at a temperature of approximately 3000 degrees Kelvin has been stretched by the expansion of space by a factor of roughly 1100, shifting it into the microwave portion of the electromagnetic spectrum and cooling it, in effect, to a present temperature of approximately 2.7 degrees above absolute zero. This relic radiation is known as the cosmic microwave background, and its discovery in 1965 by the radio astronomers Arno Penzias and Robert Wilson working at Bell Laboratories in New Jersey provided what is generally regarded as the most decisive observational confirmation of the Big Bang model as a whole. The cosmic microwave background is remarkable, among other reasons, for its extraordinary uniformity. Measured in any direction across the sky, its temperature varies by only a small fraction of 1 part in 100,000. This uniformity, as discussed in the first part of this account, presents a puzzle under the standard expansion model alone, since regions of the sky separated by great angular distances would not, without some additional mechanism, have had sufficient time to reach thermal equilibrium with one another. The theory of cosmic inflation, described earlier, offers an explanation for this observed uniformity by proposing that the entire observable universe originated from a region small enough to have reached equilibrium prior to the onset of rapid inflationary expansion. Despite its remarkable uniformity, the cosmic microwave background is not perfectly smooth. Precise measurement reveals minute variations in temperature, on the order of 1 part in 100,000, distributed across the sky in a distinctive pattern. These variations, though exceedingly small, are of considerable scientific significance, for they represent the imprint of minute density fluctuations present within the early universe. Fluctuations believed to have originated as quantum fluctuations occurring during the inflationary epoch, subsequently stretched to macroscopic scale by the expansion of space. These regions of slightly higher density, though differing from the average by only a small fraction, would go on to play a determining role in the subsequent structural history of the universe, for it was within these regions that gravity, acting over a very long period of time, would gradually draw matter together, initiating the formation of the first stars, galaxies, and the larger structures observed in the universe today. Detailed measurement of the cosmic microwave background, conducted by a succession of space-based observatories over the closing decades of the 20th century and the opening decades of the 21st, including the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite, has allowed cosmologists to determine the fundamental parameters describing the universe's composition and history with an unusually high degree of precision. These measurements indicate that ordinary matter, of the kind composing stars, planets, and living organisms, constitutes only a small fraction of the universe's total energy content, estimated at approximately 5%. A considerably larger fraction, estimated at approximately 27%, is attributed to a form of matter that does not interact with light in any manner presently understood, termed dark matter, whose existence is inferred entirely through its gravitational influence upon the motion of visible matter and upon the large-scale structure of the universe. The remaining fraction, estimated at approximately 68%, is attributed to a still less well-understood component, termed dark energy, associated with the observed acceleration of the universe's expansion over recent cosmic history, a phenomenon that will be addressed in greater detail toward the conclusion of this account. Following the epoch of recombination, the universe entered a lengthy period during which no significant sources of light existed. The first stars had not yet formed, and the universe, though now transparent, contained no luminous objects capable of illuminating it. This period, extending from approximately 380,000 years after the initial moment to somewhere in the vicinity of 100 million to 400 million years thereafter, is termed the cosmic dark ages. Throughout this interval, the only radiation present within the universe was the gradually cooling and redshifting cosmic microwave background itself. Alongside the neutral hydrogen and helium gas that filled the space between the slowly coalescing regions of enhanced density identified in the cosmic microwave background's temperature variations. It was during this quiet interval that the process of gravitational structure formation, initiated by the density fluctuations inherited from the inflationary epoch, continued its patient work, entirely unobserved by any source of light. Regions of the universe possessing a density slightly above the cosmic average continued to attract surrounding matter through gravitational influence, drawing in both ordinary matter and the considerably more abundant dark matter, which, lacking any significant interaction with light or with ordinary matter beyond gravity itself, was free to begin collapsing into concentrated structures somewhat earlier and more efficiently than ordinary matter alone. These growing concentrations of dark matter, termed halos, are understood to have formed the gravitational scaffolding within which the first luminous structures of the universe would eventually take shape, as ordinary matter, drawn inward by the gravitational influence of these dark matter halos, gradually accumulated in sufficient density to permit the ignition of the universe's first generation of stars. The universe, throughout this long and lightless interval, continued its steady expansion, its temperature falling correspondingly, its structure slowly organizing itself under the patient and continuous influence of gravity, entirely in darkness. Across a span of time considerably longer than the whole of subsequent recorded human history many times over. It is to the eventual conclusion of this dark age, and to the emergence of the universe's very first sources of starlight, that the fourth part of this account now turns. Nearly every heavier element familiar from ordinary experience, the carbon in every living cell, the oxygen drawn into the lungs with every breath, the iron carried in the blood, is often assumed to have simply been present since the universe's beginning, alongside the hydrogen and helium described earlier in this account. It was not. None of these elements existed in any meaningful quantity until stars had lived, and in many cases died, to produce them. The precise moment at which the first of those stars ignited within the universe remains a subject of ongoing investigation, constrained by the considerable observational difficulty of detecting objects at such extreme distance and antiquity. Current evidence and theoretical modeling place this event somewhere within the interval extending from approximately 100 million to 400 million years after the initial moment, a period sometimes termed cosmic dawn. Within the densest concentrations of gas accumulated at the centers of the dark matter halos described in the preceding part of this account, hydrogen and helium, drawn inward by gravity over many millions of years, are understood to have reached sufficient density and temperature to initiate nuclear fusion at their core, marking the birth of the universe's first generation of stars. These earliest stars, referred to by astronomers as population 3 stars, are believed to have differed substantially from the stars observed in the universe today. Composed almost exclusively of hydrogen and helium, entirely lacking the heavier elements that assist in the cooling and fragmentation of collapsing gas clouds in the present-day universe, these primordial stars are thought to have formed under conditions that favored the production of unusually massive objects, with some theoretical models suggesting typical masses tens or even hundreds of times that of the present-day Sun. Stars of such considerable mass burn through their nuclear fuel at a correspondingly rapid rate, and are believed to have had lifespans measured in only a few million years, a brief interval by stellar standards, before exhausting their fuel and ending, in many cases, in violent supernova explosions, or, in the case of the most massive examples, potentially collapsing directly into black holes without a luminous explosive phase at all. No confirmed direct observation of a genuine population 3 star has yet been achieved, owing to their extreme distance, their brief lifespans, and the practical limits of even the most advanced astronomical instruments presently available. Their properties are inferred instead through a combination of theoretical modeling and indirect observational evidence, including the detailed chemical composition of the oldest and most metal-poor stars observed within the present-day universe, which are thought to preserve, within their outer layers, the chemical signature of the material processed by an earlier generation of massive, short-lived stars. The successful operation, in recent years, of exceptionally sensitive space-based infrared observatories has raised the prospect of eventually detecting light from this earliest generation of stars directly, though confirmed detections have, to date, remained elusive. The formation of these first stars marks the conclusion of the cosmic dark ages and initiates a period of profound transformation throughout the universe, termed the epoch of reionization. As described in the preceding part of this account, the universe, following recombination, consisted overwhelmingly of neutral hydrogen and helium gas, electrically balanced and largely transparent to visible light, though still capable of absorbing certain wavelengths of radiation under specific conditions. The intense ultraviolet radiation produced by the first generation of massive, extremely hot stars is understood to have begun stripping electrons from the surrounding neutral hydrogen atoms, a process termed ionization, restoring the surrounding gas to the ionized state it had last occupied prior to recombination, though now at a vastly lower density owing to the intervening cosmic expansion. This process did not occur instantaneously across the universe as a whole, but rather proceeded gradually, beginning within the densest, earliest forming regions surrounding the first stars and galaxies, and spreading outward over a considerable span of cosmic time, eventually encompassing the whole of the observable universe by approximately 1 billion years after the initial moment. Regions of ionized gas, expanding outward from individual sources of intense radiation, are understood to have gradually merged with one another, in a process sometimes compared to the coalescence of individual bubbles within a rising liquid, until the neutral gas that had once filled the universe in its entirety had been reduced to only trace quantities, confined largely to the interiors of the densest, most well-shielded structures. The precise timeline and detailed physical mechanisms of reionization remain an active area of astronomical research, pursued through the study of distant quasars, whose light, having traveled across a substantial portion of the observable universe, carries within it a detailed record of the ionization state of the intervening intergalactic medium at the time that light was emitted. As the first stars completed their brief lives, many among the most massive examples are understood to have ended in core collapse supernovae, among the most energetic events presently known to occur within the universe. It is within the extreme conditions produced by these explosive stellar deaths, together with the more gradual nuclear processes occurring throughout a star's earlier lifetime, that the origin of the heavier elements is to be found. As discussed in the second part of this account, Big Bang nucleosynthesis was capable of producing only the very lightest elements, principally hydrogen and helium, together with trace quantities of lithium. Every heavier element observed within the periodic table, including the carbon and oxygen essential to known biological chemistry, the silicon and iron that compose the interiors of rocky planets, and the wide range of other elements employed throughout human technology, originated instead within the interiors of stars, or within the extreme conditions accompanying their deaths. Within the core of an ordinary star, nuclear fusion proceeds through a sequence of stages, beginning with the fusion of hydrogen into helium, the process presently occurring within the core of the Sun and responsible for the great majority of the light and heat it produces. In stars of sufficient mass, once the available hydrogen fuel at the core has been substantially depleted, the core contracts and heats further, becoming sufficiently hot to initiate the fusion of helium into carbon and oxygen. In the most massive stars, this sequence continues through further stages, producing progressively heavier elements, including neon, silicon, and ultimately iron, each stage proceeding more rapidly and at higher temperature than the one preceding it, as the star's core structure comes to resemble a series of concentric shells, each fusing a different element arranged around an innermost core of iron. Iron occupies a distinctive position within this sequence, for it represents the point at which nuclear fusion ceases to release net energy. The fusion of elements lighter than iron releases energy, while the fusion of elements heavier than iron requires an input of energy rather than releasing it, owing to the particular characteristics of nuclear binding energy across the periodic table. Once a massive star's core has been converted substantially into iron, it can no longer generate the outward pressure required to counteract the inward pull of its own gravity, and the core collapses within a period of less than a second, triggering the star's outer layers to rebound violently outward in the event observed as a core collapse supernova. It is within the extreme conditions of this explosive event, characterized by temperatures and densities considerably exceeding those achieved during the star's earlier life, that the elements heavier than iron are understood to be produced through rapid neutron capture processes that proceed far too quickly to occur under the more gradual conditions present within a star's stable core. Gold, platinum, uranium, and a considerable number of the other heaviest naturally occurring elements are understood to originate substantially through these explosive processes, and, as more recent research has established, through the collision and merger of dense stellar remnants known as neutron stars, an event first directly observed through the complementary detection of gravitational waves and electromagnetic radiation in the year 2017. The material dispersed by these stellar explosions, enriched with the heavier elements forged within the star's interior and during its explosive death, was scattered outward into the surrounding interstellar medium, where it mixed gradually with the primordial hydrogen and helium remaining from the earlier epochs of cosmic history. Successive generations of stars, forming from this progressively enriched material, inherited an increasing proportion of heavier elements, a pattern still observable today in the general correlation between a star's age and its chemical composition. It is from this long and patient process of stellar nucleosynthesis, repeated across many successive generations of stars over billions of years, that the material composing the Earth, and every organism that has ever lived upon it, was gradually assembled, element by element, within the interiors of stars that lived and died long before the formation of the solar system itself. Alongside the formation of individual stars, gravity continued its steady work upon larger scales throughout this period, drawing together not only individual stars but entire populations of them, within the growing dark matter halos described earlier, into the first galaxies. These earliest galaxies are understood to have been considerably smaller and less structured than the large spiral and elliptical galaxies observed in the present-day universe, growing over subsequent billions of years through a continuous process of gas accretion and, on occasion, through the gradual merger of smaller galaxies with one another, building, step by step, toward the diverse population of galaxies that populate the observable universe today. It is to this longer process of galactic formation and the emergence of the universe's large-scale structure that the fifth and final part of this documentary now turns. Given how much has already occurred by this point in the account, inflation, the formation of matter, the release of the first light, the ignition of the first stars, it would be reasonable to expect that the universe's story is largely complete. It is not. The greater part of the universe's structure, including the galaxy that contains the solar system and the solar system itself, had not yet formed. What follows is the account of how that final structure was assembled, and what is currently understood and not understood about where it is all headed. The processes described across the preceding 4 parts of this account, though separated from the present day by a span of time exceeding 13 billion years, establish the essential framework within which the universe's later and considerably more familiar structure would gradually take shape. This concluding part traces the continuation of that process, from the assembly of the first galaxies to the large-scale organization of matter observed across the universe today, and offers, in closing, some account of the universe's probable long-term future. Following the formation of the first galaxies, described toward the end of the preceding part, the subsequent several billion years of cosmic history were characterized by a continuous process of growth and consolidation. Individual galaxies, drawing in additional gas from their surrounding environment, continued to form new stars at a pace considerably exceeding that observed within most galaxies today. This period, generally placed within the interval extending from approximately 2 billion to 6 billion years after the initial moment, is sometimes referred to as the era of peak star formation, during which the rate of star formation across the universe as a whole is estimated to have been several times higher than the rate observed at present. Galaxies, during this period and in the billions of years that followed, are understood to have interacted with one another with considerable frequency, drawn together by their mutual gravitational attraction and by the larger-scale gravitational influence of the extended dark matter halos within which they are embedded. These interactions frequently culminated in galactic mergers, events in which 2 or more galaxies combine to form a single, typically larger structure. Such mergers are understood to have played a significant role in shaping the diversity of galactic forms observed today, contributing, among other outcomes, to the formation of the large elliptical galaxies that occupy the centers of many galaxy clusters. Structures believed to have formed through the repeated merger of numerous smaller galaxies over cosmic time. The Milky Way galaxy, within which the solar system is situated, is itself understood to have grown through a comparable history of accretion and merger, incorporating, over billions of years, the stars and gas of numerous smaller satellite galaxies, remnants of which continue to be identified today through detailed study of stellar motions within the galaxy's outer regions. Current evidence indicates that the Milky Way is presently in the process of merging with at least one smaller satellite galaxy, and that it is projected, over a timescale of several billion years, to undergo a considerably larger merger with the neighboring Andromeda galaxy, an event that, owing to the immense distances separating individual stars even within densely populated galaxies, is expected to result in remarkably few direct stellar collisions, notwithstanding the two galaxies' eventual combination into a single, larger structure. Beyond the scale of individual galaxies, matter within the universe is observed to be organized into a still larger architecture, generally referred to as the cosmic web. Detailed astronomical surveys, cataloging the positions of large numbers of galaxies across substantial volumes of space, have revealed that galaxies are not distributed uniformly throughout the universe, but are instead concentrated along extended filamentary structures, often spanning hundreds of millions of light-years in length, which intersect at dense nodes occupied by massive galaxy clusters. Between these filaments lie vast, comparatively empty regions termed cosmic voids, within which galaxies are considerably less numerous. This large-scale structure is understood to be a direct consequence of the density fluctuations imprinted upon the universe during the inflationary epoch described at the opening of this account, subsequently amplified over billions of years through the steady and patient action of gravity, acting predominantly upon the dominant gravitational influence of dark matter, within whose vast web-like distribution the visible matter of galaxies and galaxy clusters is understood to be embedded. It is appropriate, at this point, to return to a matter introduced briefly during the third part of this account, concerning the composition of the universe as presently understood. Detailed observations, drawn from multiple independent lines of evidence, including the measured properties of the cosmic microwave background, the observed motion of galaxies within clusters, and the detailed mapping of the cosmic web itself, indicate that ordinary matter constitutes only a small fraction of the universe's total energy content. The remainder is attributed to dark matter, whose gravitational influence has been essential throughout the account presented here, and to a still more mysterious component termed dark energy, associated with the observed behavior of the universe's expansion over the more recent portion of its history. For a considerable period following the Big Bang, the expansion of the universe is understood to have been gradually decelerating as the mutual gravitational attraction of matter, distributed throughout an initially denser universe, acted to slow the rate of cosmic expansion. Detailed observations of distant supernovae, conducted during the closing years of the 20th century, produced a result that was, at the time, unexpected. Rather than continuing to decelerate, the expansion of the universe appeared, from a redshift corresponding to approximately 5 billion years ago onward, to have begun accelerating instead. This discovery, recognized by the award of the Nobel Prize in Physics in the year 2011, is generally attributed to the influence of dark energy, a component whose effect, unlike that of ordinary matter or dark matter, does not diminish as the universe expands, and whose physical nature remains among the most significant unresolved questions in contemporary cosmology. Several theoretical frameworks have been proposed to account for dark energy, including its interpretation as a property of space itself, termed the cosmological constant, though a complete and confirmed physical explanation has not, to date, been established. The long-term future of the universe, insofar as it can be projected from present understanding, depends substantially upon the continued behavior of dark energy over cosmic timescales, far exceeding those addressed elsewhere in this account. Should dark energy continue to behave as presently observed, the expansion of the universe is projected to continue accelerating indefinitely, with galaxies not gravitationally bound to one another, gradually receding beyond the range of mutual observation, over a timescale extending across many tens of billions of years and beyond. Individual galaxies, and the gravitationally bound clusters to which many belong, are expected to persist for a considerably longer period, continuing to form stars from their available reserves of gas until those reserves are gradually exhausted, a process expected to extend across trillions of years, considerably longer than the present age of the universe many times over. The most massive and long-lived stars, of the kind expected to form during this extended future era, are projected to continue burning for trillions of years beyond the present, far exceeding the lifespans of the stars observed within the universe today. It is worth returning, in closing, to the material substance from which the solar system itself was formed, some 4.5 billion years ago, within a cloud of gas and dust already substantially enriched by the accumulated products of many earlier generations of stars, of the kind described in the fourth part of this account. The Sun, and the planets that formed alongside it from the same collapsing cloud of material, are composed overwhelmingly of hydrogen and helium inherited directly from the earliest moments of the universe's history, together with a smaller but essential proportion of heavier elements. Forged within the interiors of stars that lived and died over the more than 9 billion years separating the Big Bang from the formation of the solar system itself. Every element heavier than hydrogen and helium presently found upon the Earth, including the carbon within every living organism, the oxygen essential to their continued function, the silicon composing the greater part of the planet's crust, and the iron at the planet's core, originated within the nuclear furnaces of stars that completed their existence long before the Sun itself began to form. The account presented across these 5 parts traces a continuous, unbroken sequence of physical processes extending from conditions so extreme that the known laws of physics cease to offer reliable description, through the gradual cooling and expansion of the early universe, the formation of the lightest elements within its first minutes, the release of its first light after some 380,000 years, the ignition of its first stars after some hundreds of millions of years, and the patient, continuous action of gravity sustained across more than 13 billion years, in assembling the galaxies, clusters, and cosmic web observed within the universe today. It is a sequence characterized at nearly every stage by gradual and continuous transformation rather than sudden or arbitrary change, governed throughout by physical laws that remain, so far as can presently be determined, consistent across the whole of the observable universe and the whole of its recorded history. Much, it should be acknowledged plainly, remains unknown. The nature of dark matter, the underlying cause of dark energy, the precise mechanism responsible for cosmic inflation, and the conditions that may or may not have preceded the universe's earliest moment, remain active subjects of ongoing scientific investigation, pursued through continued advances in observational instrumentation and theoretical physics alike. What is presently understood, though incomplete, rests upon a substantial and mutually reinforcing body of observational evidence, gathered across many decades and through a considerable range of independent methods, and represents, at present, the most well-supported account available of how the universe observed today came to take the form that it has. It is worth returning, briefly, to where this account began, a single sentence, of the kind found in a school textbook, describing the universe's origin as a kind of explosion. What has been traced across these 5 parts is, in fact, a far more orderly and far more precisely understood sequence than that single sentence could ever convey. A sequence in which the very hydrogen once present in the earliest instance of existence now sits, quietly, within every glass of water, in which the carbon forged inside a star that lived and died billions of years before the Sun ever formed, now composes the greater part of every living thing, and in which the faint microwave light released some 380,000 years after the beginning, still, at this very moment, passes through the room in which this is being heard. This concludes the account. The universe, across the whole of the history traced here, has continued, and continues still, its slow and steady expansion, carrying within it the light of galaxies formed billions of years ago, the elements forged within stars long since ended, and the quiet, ongoing consequences of a sequence of events set in motion in the smallest possible fraction of a second, at the very beginning of time itself. Thank you for spending this time with it. Rest well.